So we implied that orbital forcing is because of changes in the orbital parameters like obliquity, ellipticity, and eccentricity. But what are the other forcings at shorter time scales in the system? Obviously, you already heard of global warming and humans creating forcing. So in this sense, forcing always means something that changes the radiation balance of the system. So if you look at the top of the atmosphere, energy is coming from the sun and some energy is being sent back by the Earth system. And under global warming, obviously we are creating an imbalance where we are not sending back all the energy, we are trapping more of the energy, so we are warming up. And on the time scales we are interested in terms of impact on human evolution, we need to revisit some of these things. You will see many such radiation balance figures. I have energy balance podcasts elsewhere in my courses that you can look up. Just to go briefly through this here, incoming solar radiation in shortwave. We typically talk about shortwave radiation and long wave radiation. Visible light energy that's coming in from the sun is all in the shortwave mostly, and the energy that the Earth sends out is in the so-called long wave. It's like the thermal energy from our skin, which we cannot see, but you can feel. Or imagine a pot sitting on a stove. It's hot, but unless you go near, you don't necessarily see that it's warm unless you heat it to a very high temperature, in which case it can also reach temperatures to emit light at various wavelengths like the sun. Okay, so there is 340 watts and you can see the range in the present day, and the atmosphere absorbs some of it. A lot of it reaches the surface, and surface itself then emits some back. So about 30% of the incoming solar energy is reflected back to space without doing anything. This is the albedo that we talk about. So that's about 30% in the current climate. With climate change, we are changing various things with urbanization, deforestation, agriculture, and of course cloud properties, etc. are changing, so that is bound to change the albedo a little bit. But whatever energy remains at the surface is absorbed and is creating evaporation, sensible heat exchange, and there is thermal energy going out. What needs to happen, of course, is a balance between incoming solar radiation and outgoing thermal radiation at the top of the atmosphere, and global warming is caused by an imbalance between them. So here you can see that the numbers here are much larger than what's coming from the sun, because this is like having a blanket. You trap your own body's heat to create warmth and reduce the cold you're feeling. That's a similar thing here. Earth has a greenhouse blanket which traps the energy and bounces it back and forth to create peaks that are larger than the energy coming in. So you have atmosphere that is opaque to this outgoing long wave. So from the surface you are emitting 398, 342 is bouncing back, and what escapes out of the system is 239 to balance this. So this is what we are always interested in terms of how this has changed over time. Okay, what changes that? There are so-called natural forcings, and now we have anthropogenic forcing. Natural forcings are, of course, the albedo changes because of glaciation and deglaciation. We'll look at the feedbacks in a little bit. And of course, volcanic forcing. Volcanic forcing acts on many time scales depending on how it is done. It is obviously a very fast time scale emission which puts out lots of aerosols and chemicals like sulfur dioxide, ash, HCl, hydrochloric acid, which can form clouds and spread throughout the Earth's atmosphere, depending on where it is emitted and how high in the atmosphere, and so on and so forth. The most direct impact is always a cooling. We will see that in a minute. So surface cooling almost always occurs if there is a substantial emission from a substantial eruption of a volcano, and if it gets into the stratosphere it can stay around for a long time. Without going into detail, stratosphere is well stratified, and it doesn't have much weather or rain to remove what is put into the stratosphere. And in fact, those are the ideas being tossed around to see if we can put aerosols into the stratosphere to reduce global warming and so on. So without digressing too much, the volcanic eruptions can last for a while, depending on, again, whether it's in the stratosphere or the troposphere, or it can get rained out pretty fast. So the removal processes include cloud modifications, nucleation, particle growth, and of course they also impact outgoing long wave radiation and can have warming. In the beginning they can have increased planetary albedo and cooling, and also reduced solar radiation and cooling and so on. So what exactly happens depends on things like this. This is a simulation of the Toba volcanic eruption that happened maybe about 75,000 years ago and had a super volcanic eruption that had massive impacts. So you can see that the model is simulating a drop in temperature that's substantial and out of the range of natural internal variability. So the cooling tends to be much larger depending on how much material is put out, and you can see the time scale here in terms of range of temperatures. Precipitation also drops. So typically when volcanic eruption happens, there is increased droughts. So reduced sunlight, cooling and reduced precipitation together can create massive drops in crop yields and so on, as has happened even in the last couple of centuries many times. Okay, but if you move away, so this was over Sumatra. If you look at the Indian region, for example, air temperature cooled, but then it bounced around and recovered fairly quickly compared to where the volcanic eruption happened overall. And precipitation change, you can see that can remain within natural variability depending on where you are looking, globally or just in the neighborhood. So how the system adjusts may depend, and it is also comparing other strong El Niños, moderate El Niños, and neutral conditions, moderate El Niño, La Niñas and strong La Niñas, and the ensemble mean, just to make sure that we are actually talking about impact of a volcano and not other natural variabilities or volcano-induced natural variabilities. There is some debate that volcanoes can trigger El Niños, but I don't want to go there anyway. So in extensive glaciation periods like snowball Earth episodes which have happened, most of the Earth will be covered by glaciers. So CO2 can get trapped and continue the cooling and amplify the cooling that led to the glaciation. But what happens is that the volcanoes keep going off and they keep putting CO2 into the atmosphere. CO2 is not mentioned here, but there is buildup of CO2, and that buildup can then terminate the extensive glaciation into low latitudes like during snowball Earth episodes and return the system back to normal. So volcanoes can have all kinds of roles to play, and they have also been invoked in the so-called Little Ice Age that happened after the end of the medieval warm period in the 11th, 12th, 13th century and terminated at about the beginning of the Industrial Revolution. Other natural variabilities, of course, that the sun's output itself changes. So this is a calculation reconstructions from long-term solar irradiance. So watts per square meter. You can see the numbers, a couple of watts per meter squared changes using a different solar magnetic flux model and long-term trend from modeling sun-like stars. And as we have argued before, there are small variations in solar radiation even into the 20th and 21st centuries, and people have tried to use these to argue that global warming is caused by energy output from the sun, but obviously calculations clearly show that that's not the case, that warming is indeed related to human forcing, which include things like this. So if we go back to the 18th century, effective radiative forcing, so the net change in the top of the atmosphere balance versus anthropogenic effective radiative forcing, you can see that there is the solar tiny bit of fluctuations up and down. Black carbon on snow and contrails can change the albedo of the snow, and contrails are what are left by ships and planes, which can affect incoming solar radiation versus outgoing long wave radiation and can cause warming. Black carbon is absorbing aerosol, of course. Stratospheric water affects radiation balance, which are related to human activities and warming. Tropospheric ozone, again pollution from human activities, is a very strong greenhouse gas. In the stratosphere, it's absorbing UV and protecting us, whereas in the troposphere, it's a killer, bad for health, bad for crops, and bad for global warming. Other greenhouse gases, man-made greenhouse gases, CO2, of course. Aerosols can be cooling. Aerosol cloud interactions can also be cooling. So aerosols have what are called direct effects of changing radiation by scattering solar radiation, for example. They have indirect effect where they affect cloud microphysical properties like cloud droplet size, condensation, cloud condensation nuclei, and can change cloud optical properties and can end up cooling. And of course, land use is how we change forestation, albedo, urbanization, albedo, and stratospheric ozone, and volcanic eruptions, which are these pulses, which are can be large pulses but very short in duration. Okay, so here is a combination of natural forcing like solar radiation, stratospheric ozone, and man-made forcings as well, which include all these warming agents. Okay, so people do compute the net forcing, global mean radiative forcings since 1750. You can see when this is in this direction, we are trapping more energy. When it is in this direction, we are cooling. So you have cloud adjustments from aerosols, NOx, and albedo changes due to land use. Forests can be darker than urban areas, deforested areas, and so on. And you have here the total anthropogenic forcing, a combination of CO2, methane, halocarbons, N2O, and carbon monoxide, and non-methane volatile organic compounds. Okay, so obviously they are much larger than natural variability in solar radiation or solar irradiance, which is not causing the warming. It's a very tiny part and not a major part. Okay, so here is another way to look at it, how we have increased the warming influence in watts per square meter since the 1980s. This is the annual greenhouse gas index. Carbon dioxide is of course the most dominant greenhouse gas. Methane, nitrous oxide, CFCs, and others like HFCs, N2O, N2O is here, but others. When we look at greenhouse gases, we have to look at their concentrations, their lifetime or residence time in the atmosphere, and the so-called global warming potential. We typically peg CO2 as a global warming potential of 1 for each kilogram increase of CO2, how much warming happens, versus methane, which is about 25 times N2O, which is a couple of hundred times nitrous than CO2, and so on. Methane only has a residence time of about 10 years. Nitrous oxide has a residence time of a couple of hundred years. Carbon dioxide can have multiple centuries depending on what box of the carbon you are looking at. Okay, so we'll leave this here in terms of forcings and come back and look at role of the oceans before we go on to look at other aspects like modeling of the impact of humans and changes in forcing over time, even in the past. Okay, so let's leave it here.